students, welcome to our YouTube channel Experience Tutor. Today we'll discuss Class 12th Physics Current Electricity Chapter 3 NCERT Solution Part 3. Our mission is to provide free classes on YouTube for all students of Class 6 to Class 12, special classes for the student preparing for IIT, JEE, NEET, NDA and other competitive examinations. Before we begin, we have a small request for you. Please subscribe, like and share our channel. Please click on the subscribe button to support us and also click on the bell icon to get automatic notification whenever a new video is uploaded by us. Let us start today's lesson. In the last class, we have done till problem 3.10. In today's class, we'll do 3.11. A storage battery of EMF 8 volt and internal resistance 0.5 ohm is being charged by a 120 volt DC supply using a series resistor of 15.5 ohm. What is the terminal velocity of the battery during the charging? What is the purpose of having a series resistor in a charging circuit? Let us see the solution. EMF of storage battery E is equal to 8 volt. Internal resistance of the battery R is equal to 0.5 ohm. DC supply voltage V is equal to 120 volt. Resistance of the resistor R is equal to 15.5 ohm. Effective voltage of the current V dash is equal to V dash. R is connected to the storage battery in series, hence it can be written as V dash is equal to V minus E. V dash is equal to, putting the value of V and E as 120 and 8, we get 120 minus 8, that is 112 volt. Current flowing in the circuit is equal to I, which is given by the relation I is equal to V dash upon capital R upon plus small r. So putting the value of V dash as 112, capital R as 15.5, small r as 5, we get 112 upon 16, that is 7 ampere. Voltage across the resistor R is given by the product IR, that is 7 into 15.5, that is 108.5 volt. DC supply voltage, terminal voltage is equal to terminal voltage of the battery plus voltage drop across R. Terminal voltage of the battery is equal to 120 minus 108.5, that is 11.5 volt. A series of resistors in a charging circuit limits the current drawn from the external source. The current will be extremely high in its absence. This is very dangerous. And this is the overall answer for this problem. Let us move to the next problem. Now we'll do 3.12. In a potentiometer arrangement, a cell of EMF 1.25 volt gives a balance point at 35 cm length of the wire. If the cell is replaced by another cell and the balance point shifts to 63 cm, what is the EMF of the second cell? Let us see the solution. EMF of the cell E1 is equal to 1.25 volt. Balance point of the potentiometer L1 is equal to 35 centimeter. The cell is replaced by another cell of EMF E2. New balance point of the potentiometer L2 is equal to 63 centimeter. The balance condition is given by the relation E1 upon E2 is equal to L1 upon L2. E2 is equal to E1 multiplied by L2 upon L1. Putting the value of E1, L2 and L1 as 1.25 into 63 upon 35, we get 2.25 volt. Therefore, EMF of the second cell is 2.25 volt. Let us move to the second question. Next question. Now we'll solve problem number 3.13. The number density of free electrons in a copper conductor estimated in example 3.1 is 8.5 into 10 to the power 28 meter per cube per meter cube. How does how long does an electron take to drift from one end of a wire 3 meter long to other end? The area of cross section of the wire is 2 into 10 to the power minus 6 meter square and it is carrying a current of 3 ampere. Let us see the solution. Number density of free electron in a copper conductor N is equal to 8.5 into 10 to the power 28 meter per meter cube. Length of the copper wire L is equal to 30 meter. Area of cross section of the wire is equal to 2 into 10 to the power minus 6 meter square. Current carried by the wire I is equal to 3 ampere, which gives by the relation I is equal to NAEVD. E is electric charge 1.6 into 10 to the power minus 19 coulomb. Vd is equal to direct velocity is equal to length of the wire L upon time taken by the to cover the length, that is T. Therefore, I is equal to NAEL upon T. T is equal to NAEL upon I. Putting the values of NAEL upon I and I, we get 2.7 into 10 to the power 4 seconds. Therefore, the time taken by an electron to drift from one end of the wire to other end is 2.7 into 10 to the power 6 10 to the power 4 second. Let us move to the next sum. Let us move to the next sum 3.14. These are the additional sums of the exercise. The Earth's surface has negative surface charge density of 10 to the minus 9 coulomb per meter square. The potential difference of 400 kV between the top of the atmosphere and the surface results due to the low conductivity of the lower atmosphere in a current of only 1800 ampere over the entire globe. If there were no mechanism to sustain the atmospheric electric field, how much time roughly would be required to neutralize the Earth's surface? Radius of the earth is given 6.37 into 10 to the power 6 meter. So surface charge density of the earth sigma is equal to 10 to the power 9 coulomb per meter square. Current over the entire globe I is equal to 1800 ampere. Radius of the earth R is equal to 6.37 into 10 to the power 6 meter. Surface area of the earth A is equal to 4 pi square. Putting the value of R, that is 4 into 3.14 into 6.37 into 10 to the power 6 whole square is equal to 5.09 into 10 to the power 14. On calculation, we got this much. Charge on the Earth's surface Q is equal to sigma into A. Putting the value of sigma as 10 to the power 9 and A as pi 5.09 into 10 to the power 14, we get 5.09 into 10 to the power 5 coulomb. Time taken to neutralize the Earth's surface is equal to T. I is equal to Q by T. T is equal to Q by I. So putting the value of Q and I, we get 5.09 into 10 to the power 5 upon 1800. Upon solving this, we get 282.77 seconds. Therefore, the time taken by the to neutralize the Earth's surface is 282.77 seconds. Let us move to the next sum. The next sum is 3.15. A. 6 lead acid type of secondary cell, each of EMF 2 volt and internal resistance 0.015 ohm are joined in series to provide a supply to a resistance of 8.5 ohm. What are the current drawn from the supply and its terminal voltage? B. A secondary cell after long use has an EMF of 1.9 volt and a large internal resistance of 380 ohm. What maximum current can be drawn from the cell? Could the cell derive the starting motor of a car? Let us see the solution. The solution for part A is number of secondary cells, that is n is equal to 6. EMF of each secondary cell R is equal to 0.015 ohms. Series resistor is connected to the combination of cells. Resistance of the resistor R is equal to 8.5 ohm. Current drawn from the supply is equal to I, which is given by the relation I is equal to Ne upon R plus Nr. Putting the value of Ne capital R small r, we get 2 into 6 into 2, 8.5 plus 6 into 0.015. Upon solving, we get 12 upon 8.59. Upon solving, we get upon solving, we get 1.39 ampere. Terminal voltage V is equal to IR, that is I is 1.39 into R is 8.5, that is 11.87 ampere. Therefore, the current drawn from the supply is 1.39 A and terminal voltage is 11.87 A. Part B. After a long use, EMF of the secondary cell E is equal to 1.9 volt Internal resistance of the cell small r is equal to 380 ohm. Hence maximum current, that is E upon R, can be written from that, and putting the value of E and R 1.9 upon 380, that is 0.005 ampere current will be withdrawn. Therefore, the maximum current drawn from the cell is 0.005 ampere. Since a large current is required to start a motor of a car, the cell cannot be used to start a motor. Let us move to the next sum. Now we'll see problem 3.16. Two wires of equal length, one of aluminium and other of copper, have the same resistance. Which of the two wires is lighter? Hence explain why aluminium wires are preferred for overhead power cables. Rho aluminium is equal to 2.63 into 10 to the power 8 ohm meter. Rho copper is equal to 1.72 into 10 to the power 8 ohm meter. Relative density of aluminium is 2.7 and of copper is 8.9. Let us see the solution. So relative density of aluminium rho, resistivity of aluminium rho Al is equal to 2.63 into 10 to the power minus 8 ohm meter. Relative density of aluminium D1 is equal to 2.7. Length L1 be the length of the let L1 be the length of the aluminium wire and M1 be its mass. Resistance of the aluminium wire R1 is equal to R1. Area of cross section of the aluminium wire is equal to A1. Resistivity of copper rho Cu is equal to 1.72 into 10 to the power minus 8 ohm meter. Relative density of the copper D2 is equal to 8.9. Let L2 be the length of the copper wire and M2 be its mass. Resistance of the copper wire is equal to R2. Area of cross section of the copper wire is equal to A2. The two relations can be written as R1 rho 1. R1 is equal to rho 1 L1 upon A1, that is equation 1. R2 is equal to rho 2 L2 upon A2, that is equation number 2. It is given that R1 is equal to R2. Therefore, rho 1 is up L1 upon A1 is equal to rho 2 L2 upon A2. And L1 is equal to L2. So we get rho 1 upon A1 is equal to rho 2 upon A2. Then we can write the same as A1 upon A2 is equal to rho 1 upon rho 2. Putting the value of rho 1 and rho 2, we will get 2.63 upon 1.72. Mass of the aluminium where M1 is equal to volume into density, which we can write volume can be written as A1 L1 into D1. A1 L1 into D1 is equal to equation 3. Mass of the copper wire M2 is equal to volume into density. Volume can be written as A2 L2 and density can be written as D2. Therefore, A2 L2 D2 is equation 4. Dividing equation 3 by equation 4, we obtained m1 upon m2 a1 l1 d1 upon a2 l2 d2. For l1 is equal to l2, m1 upon m2 is equal to a1 d1 upon a2 d2. For a1 upon a2, we get 2.63 upon 1.72. Therefore, m1 upon m2 is equal to 2.63 upon 1.72 into 2.7 upon 8.9. We get the solution as 0.46. It can be inferred from this ratio that M1 is less than M2, hence aluminum is lighter than copper. Since aluminum is lighter than copper, it is preferred for overhead power cable over copper. Let us see the next problem. Now we'll solve problem number 3.17. What conclusion can you draw from the following observation on a resistor made of alloy manganese? So in the tabular form, the value of current A, voltage V, current A and voltage V are given. It can be inferred from the given table that the ratio of voltage with current is constant, which is equal to 19.7. Hence, manganese is an ohmic conductor, that is, the alloy obeys Ohm's law. The ratio of the voltage with the current is the resistance of the conductor. Hence, the resistor of manganese is 19.7 ohm. Let us see the next problem. Now we'll solve problem number 3.18. Answer the following question. A. A steady current flows in a metallic conductor of non-uniform cross-section. Which of these quantity is constant along the conductor? Current, current density, current field, drift speed. When a steady current flows in a metallic conductor of non-uniform cross-section, the current flowing through the conductor is constant. Current density, electric field, and drift speed are inversely proportional to the area of cross-section. Therefore, they are not constant. Current density, electric current, and drift speed are inversely proportional to the area of cross section. Therefore, they are also not constant. Now, let us solve the part B. Is Ohm's law universally applicable for all conducting elements? If not, give examples of elements which do not obey Ohm's law. Answer is no. Ohm's law is not universally applicable for all conducting elements. Vacuum diode semiconductor is a non-ohmic conductor. Ohm's law is not valid for it. Now let us see part C. A low voltage supply from which one needs high current must have very low internal resistance. Why? So solution to the part C is, according to Ohm's law, the relation for the potential is V is equal to IR. Voltage V is directly proportional to the current I. R is the internal resistance of the source. I is equal to V upon R. If V is low, R must be very low, and so that high current can be drawn from the source. Now we'll see part D. A high tension HT supply of say 6 kV must have a very large internal resistance. Why? In order to prohibit the current from exceeding the safety limit, a high tension supply must have a very large internal resistance. If the internal resistance is not large, then the current drawn can exceed the safety limit in case of a short circuit. Now let us see question number 3.19. Choose the correct alternative. A. Alloy of a metal usually have greater or less resistivity than that of their constituent metals. A. Solution of part A is alloy of the metal usually have greater resistivity than their constituent metal. It is correct. Now part B. Alloy usually have much lower or higher temperature coefficient of resistance than pure metals. Alloy usually have lower temperature coefficient of resistance than pure metals. It is also true. Part C is the resistivity of the alloy manganese is nearly independent of increases rapidly with increase of temperature. The answer to this is C. The answer to C is the resistivity of the alloy manganese is nearly independent of increase of temperature. Now part D. The resistivity of a typical insulator, that is amber, example amber, is greater than of a metal by a factor of the order of 10 to the power 22 upon 10 to the power 3. Solution to this problem is the resistivity of a typical insulator is greater than of that of a metal by the factor of 10 to the power 22. And this is the end of today's class. Before we close the session, we request you to subscribe, like and share our channel and this video among your friends and relatives. Please click on the subscribe button to support us and also click on the bell icon to get automatic notification whenever a new video is uploaded by us. Thank you for supporting us and watching our videos. Thank you very much.